Hey guys, welcome to another episode of Getting School. In this video, we're going to talk about leap years, more specifically why they exist and why we need them. If I asked you why a leap year has 366 days as opposed to a normal year that has 365 days, you're probably going to answer it's because in a leap year like 2016, February has 29 days, whereas in a normal year like 2017, February has only 28 days. If I asked you again why does February of 2016 has a day more than that of February of 2017, you're probably gonna answer, well, it's because 2016 is divisible by 4 and 2017 is not divisible by 4. That's it, right? Well, it's not. It's not that simple. So the whole concept of leap year has something to do with the Earth's revolution around the Sun. Let's assume this arrow is a longitude, or a point, or even you on Earth, where the Sun is directly above you. That is, you are facing the Sun dead straight, looking him in the eye. Now when the Earth rotates about its own axis, it completes a 360-degree rotation. We call it a sidereal day, which is 23 hours, 56 minutes and 4.1 seconds long, which is approximately 4 minutes less than 24 hours. The only complication here is that even after the Earth has completed a 360-degree rotation, the arrow, which is you, will not be facing the Sun directly in the eye again. This is because the Earth has moved some distance in its orbit around the Sun. Now the arrow to face the Sun again, the Earth needs to rotate a little bit more. Now this is called a solar day. Time it takes for a point on Earth to directly face the Sun again after a rotation about its own axis. Now this solar day is also not exactly equal to 24 hours, because that small rotation that the Earth takes to complete a full solar day from a sidereal day, see, that varies depending upon where the Earth is in its orbit around the Sun. This is because the Earth's orbit around the Sun is not a circle, it's an elliptical orbit. So sometimes in its orbit, the Earth is far closer to the Sun as opposed to sometimes when it's much farther away. Now let's suppose the Earth is somewhere in the orbit nearer to the Sun. Now when it's nearer to the Sun, the time it takes for the Earth to rotate from a sidereal day to complete a full solar day is longer because it has a bigger angle to rotate. Contrary to when it's far away from the Sun, it has a smaller angle to rotate, consequently needing less time to complete the rotation. That's why a solar day could be 24 hours and 1 minute, or 23 hours and 59 minutes, or some other variation with respect to 24 hours. In the end, compromise defined a normal day as a period of 24 hours. But those extra seconds or minutes of time we might not have counted will come to haunt us later, because see, even if the Earth completes a 365-day revolution around the Sun, in which each day is exactly 24 hours, Earth's angular position with respect to the Sun is not back to where it was originally when the Earth started its journey around the Sun. So to come back to its starting position, or for the arrow, which is you, to be facing the Sun directly again, the Earth needs to rotate about its own axis a little bit more. This takes a time of about 0.2421 days. That's why a year, or a solar year, has 365.2421 days, which is approximately 365.25 days. But we neglect that 0.25 fraction for now and define a year as a period of exactly 365 days. But that 0.25 fraction of a day amounts to a whole day in 4 years of time. This is where the leap year concept comes in. To balance the calendars, we add this day to every 4th year, calling it a leap day, and the year is a leap. That's the reason why 2016, 2020 and etc. are leap years. And this is where the divisible by 4 rule comes from. But hold on, this rule is not true for all years. For example, a century year. Remember when we said that a solar year is actually 365.2421 days and not exactly 365.25 days? Which means we are adding up to 0.01 day per year to the calendar. That means by adding a leap year every 4 years, we are essentially adding an extra day to the calendar every 100 years. So to balance the calendar back again, we remove a day every 100 years, which means we don't add a leap day to the calendar for the year example of 180, even though it comes 4 years after 9680, which is a leap day. That is why we don't make century years as leap years, which is the reason for 1900, 1800 or 1780s not being leap years, even though they are divisible by 4. But what happens when we go on removing a day every 100 years? Then we would be falling short of a day every 400 years. Now coming back to the solar year, its actual time period is 365 days, 5 hours, 48 minutes and 46 seconds. But we assume it as 365 days and 6 hours, which is equal to 365.25 days. Which means we are adding up to 11 minutes and 14 seconds to the calendar every year, or 674 seconds to be precise. Now these 674 seconds constitute to 269,600 seconds in 400 years, which is approximately equal to 3 days, which means we are adding up to 3 days every 400 years. It is rectified, as I mentioned earlier, by not making century years as leap years. This is another way of explaining why we remove 3 days each from 180, 280 and 380 to balance the calendar and rectify this problem. Now since this problem of adding 3 days every 400 years is already rectified, if we remove a day again for 480, we would be falling short of a day. That's why 480 gets back its leap day and becomes a leap year. Because if we don't make 480 a leap year, we would be falling short of a day. So every 400th year is a leap year. This is where the divisible by 400 rule comes in. This is the reason why 1280, 1680 and 2080 are leap years. But even now we are adding up to 30 seconds per year to the calendar, which will cause a problem so far in the future for future generations, which are millennia away. So we don't need to worry about it right now. Now to the question of why we really need a leap year or a leap day every 4 or 400 years. It's, as I said, to balance the calendar. If we don't add a leap year every 4 years, then our calendar will be behind 25 days in 100 years, which is almost a month. And with this will add up to another 2 months in 200 years, and so on, and eventually falling behind the seasons and making it harder to predict them. We might end up with winter in May and summer in December. And this would be painful for the average farmer who depends entirely on the exact occurrence of seasons for harvesting his crops. So there we go. Hope you guys learned something about leap years and why we really need them. If you like this video, please like, comment and subscribe for more. Thanks for watching. As always, see you next time.